Okay, so we start on page 32 of our green books on the transformers. So this section is called Transformers and Power Distribution because the whole idea of a transformer is to step up or step down voltage as we discovered yesterday. And what's that going on now? Oh, it's a battery, so I might just pause. Okay, so let's define the transformer. So the way to define the transformer simply is to say that a transformer is a device that, it's wrong colour, don't do that. It's a device that steps up or steps down AC voltage at the same time it alters the current. So the definition, it's a device, an electronic device, which steps up, increases, or steps down AC voltage at the same time current is altered. Okay? And the way that it will work is that it works by using the magnetic field from one coil, as we saw yesterday, and transferring that change of flux into the other. So we're just taking this top line down at the moment. So we're not going to copy the whole of this. I'll actually supply this. This is actually on the Moodle for you anyway. You can access this. This is just a summary of the textbook. Okay? So let's have a look at some of the features of that statement. So the statement, firstly, is it steps up and steps down. So we have two different types of transformers. A step up and a step down. Now the symbols for each of these transformers are the following. A step up, the symbol is looking like this. Undo that. It's not a hand.
Is it a coil?
Yes, it's a coil. Okay, so the symbol is a step up, that's it there. Now this is the primary coil, and we know from yesterday that a transformer consists of two coils of wire. The first is the primary coil, and the other one is called the secondary coil. Okay, now the symbol for primary is a 1 with a 0, and the symbol for secondary is 1 with a degree, also known as 1 degree and 2 degree. Primary, first degree, secondary, second degree. Okay? So what does a step up do? It increases voltage. Now this is the electronic symbol. We know that if we were drawing a circuit, don't draw this please. If I was drawing a circuit and I came across this symbol here, or whatever, we know that this symbol up here represents a resistor. This here represents a voltmeter. Obviously you wouldn't put a voltmeter in series. So this is the symbol that you would use if you were putting it in a circuit. You would go or whatever, and that would because it's the electronic symbol that we're using, okay? So don't overly worry too much what I'm doing here. Okay, now what does it do is if I apply, say, 10 volts to the primary coil, I have to get a higher voltage in the, say we'll go 40 volts in the secondary coil. So the increase of voltage occurs. Okay? So if this is a times by 4 voltage, okay, then something else has to, because we can't just create or destroy energy, something has to also decrease by a factor of 4. And what is it? It must be current. So if we increase the voltage by a factor of 4, what will happen here will be that, just say we had 2 amps, let's make it a nicer number. Let's say we had 8 amps in this one here, it would decrease to 2 amps. Notice that in the primary coil, if you multiply current and voltage, then it equals 80. And if you multiply current and voltage in the secondary coil, it stays as 80. Okay? And I'll explain why that happens in a few more moments. Okay? So that's what a step up does. Step up increases voltage. At the same time, it must decrease what's it? Current. Good. And we'll work out why this increase of one requires a decrease in the other when we come to the conservation of energy. Obviously, you can't create energy out of nothing. Right, so a step up increases voltage. What would a step down do? Right, it decreases. And the symbol is this one. Oops, too many. So the primary coil is here, and the secondary coil is here. And we know that this decreases voltage. So if this was 100 volts on this side, and it became 20 volts on this side, then it's a divide by 4 step down in voltage. But can we just decrease voltage? If voltage decreases, something must also increase to balance the equation. So what must increase? Current. Good. So let's just make up some numbers. Let's make the current as being 2 amps on this side. What will, if the voltage decreases by a factor of 4, what will the amperage have to increase by? 4, so it would become 8 amps. Notice once again, if you multiply the numbers on each side. Thank you very much. Can I just change that to be a 25 there, and that would make this work nicely. So rather than having rub out everything, I've just got to move one number. Okay? Yeah, so if I multiply here 100 by 2, you get 200. And over here, 25 by 8 is also 200. And we'll come back and say, why is he multiplying these together? Okay? Right, so let's just have a look at how this happens and why it happens. So we've got the two ideas of a step up and a step down. What makes a step up, and what makes a step down, step down? It's just simply to do with the symbol I'm using. What do you notice about the primary and secondary coil? It's got one is bigger than the other. Good. So it's the number of windings. Rather move that. So the number of windings ratio, determines whether or not it steps up or steps down. So let's have a look at two examples. Example 1. If I've got a coil over here which has 100 windings in it, okay, and it's been placed beside another coil which has 20 windings. Actually, I might just put a ball in front of that. Now, remember, I have to tell you which is the primary coil. The primary coil is the coil to which you put in the voltage. The secondary coil is the one which puts out the voltage. So this is the primary, and this is the secondary. Okay. Which coil has the greater windings? The primary. Okay. So this means that this one here, the primary is bigger than the secondary. This would step down. This is a step down. And what will be the factor of the step down? It's a divided by 5. So the number of windings determines whether it steps up or steps down, and by how much. So all I've got to do is work out the ratio between them. Okay. Second example, primary coil here has 25 windings. The secondary coil over here has 50 windings. So again, I'll make it as n equals 50. Okay, even though I've drawn the two coils the same size, they may be the same size physically, but one can have much more windings than the other simply because the wires in one are bigger or thicker or thinner. Okay? So, would this step up or step down?
Up.
Right, it would step up. Okay? And what's the factor of the step up? A times by 2. Now remember, the factor of the step up or step down acts on what? The voltage only. Good. Not the current. The current has to do the exact opposite. Okay, so that's the first one. So let's work out simply what is going to happen here. So example 3, we're going to calculate. We're going to actually do some calculation then. Okay, we've got a transformer. In this transformer, I'm not showing the structure of the transformer, I'm just showing the symbol. We know that the transformer, from the way we did it yesterday, normally a transformer is a big metal thing which has a massive iron core, which is laminated, and the two coils are side by side, very close to each other, and we use the soft iron laminated core to try and direct flux from one to the other. So I am here just doing it symbolically so that we can do a calculation. Rightio. Firstly, we determine whether or not this is a step up or a step down. The primary coil has 90, the secondary coil has 30. Is it a step up or step down?
Yeah.
Down. What's the factor? What's the factor from going one to the other?
3.
It's a 3. So this, because it's a step down, it divides by 3. So the voltage will be divided by 3, and that will give us 70 volts. Okay? Are we happy with that? Now, if the current in this coil over here was 0.2 amps, what would happen to the current at the same time? Right, it would times by 3 and you would get 0.6 amps. Now, why does the amperage times the voltage on both sides have to be equal? And it comes from something we did in the preliminary course, which says that the electrical energy in a circuit, E, is given by power times time, okay? PT. And we know that power equals voltage times current, the IV formula, or VI formula, whatever you want to say. Now, if we take time being 1 second, then E and P would be the same value. But we know power is measured in what? Watts. Watts, good, yes. And E is measured in joules, good, okay. Remember, watts is just joules per second, okay. So if we just take 1 second, then the amount of power equals the amount of energy in the coil. Okay, so if we say, okay, let's see how much energy is in both coils at the same time in 1 second. In 1 second, you would be able to generate that times that, which is 210 volts times 0.2 amps. When you multiply that, that becomes 42 watts. Okay? So in 1 second, you generate 42 watts of energy in the primary coil. Now, can you create or destroy energy? No. So if all the energy is transferred from the primary coil into the secondary coil, how much energy must be over here? 42 watts. So that means 70 times the 0.6 must still equal 42 watts. If you multiply those out, yes, it does. It equals 42. Okay? Can I get more? If this is 42, can I get 80 over here? No, we'll be breaking the law of what law? Conservation of energy. Good. Can I get less than 42 watts? Yes, and there's a reason for it. If all the flux from the primary coil doesn't go into the secondary coil, but some leaks out, like over here, will we get all the energy in the primary coil going into the secondary coil? No. So, in a modern situation, we are getting really close to being 100% from one to the other. But we still have a slight bit of flux leakage. Okay? So this is not exactly 42. But some of our transformers are up to 98% efficient, which are getting really, really good. Okay? So we aren't losing too much energy. We call this situation, when you're doing it theoretically and both sides are equal, we call this an ideal transformer. Okay? A non-ideal transformer, which is a real-world transformer, there is always heat generated or loss of flux. So we lose energy by two forms. It's loss of flux, because the flux leaks out, or we generate heat because of eddy currents. And that's lost energy. How can we make the transfer of energy from the primary coil over here to the secondary coil over here as efficient as possible? Well, we minimise loss of flux, but we also have to minimise heat. And what do we do to minimise heat now? We laminate the core. However, in really, really large transformers, we still, even though we laminate the core, we do as much as possible to stop leakage, we still get heat generated. It will always happen. So this will actually always heat up. So we make sure that if we are using a transformer, the transformer is in a position in the machine or in the device, in our TV or in our microwave, which it's not going to melt other things around it because it gets hot. And we've all done, I'm picking up this here. I'm feeling it. What am I feeling? Heat. It's hot. Why is it hot? Because I am losing energy from this. Okay? So they're going to heat up. Now, it's not too bad here because this is not hot enough to melt this thing. But imagine we have to use a massive transformer where the heat is really going to start melting. So we have to somehow find methods of getting rid of the heat. So we have things like fans being placed into machines to cool them down. And in really big ones, we have oil that is pumped around, like oil gets pumped around your engine to transfer energy and heat away, pick it up, and then get cool somewhere else. Okay? So we get back to them, and they're the commercial big heat, transformers that we use in power distribution. Are we okay with why a transformer works? Okay. So let's take an example. I'll just hand out until then you can read it off the board. Okay, so worksheet 3A, the ideal transformers thing. Number one, now we've got a diagram of a transformer over here. Here's a nice diagram, a diagram to show the two sides. We need one coil of wire, and we've got one coil of wire on this side over here. This coil over here is attached to, what's this symbol over here say? What's that? What's that say? That symbol, I'll draw it a bit larger for you because you probably, like that. It's a power source which is alternating. So this symbol over here with a circle with a symbol, that's supposed to be a sine curve in there, is a symbol for alternating current. Okay? Now, my question to you is, why does a transformer require alternating current? Right, good. We need alternating current because what is formed over here? This is a coil of wire. A coil of wire, as Becca told us last week, we place it with a current through it, is called a, same with S, solenoid, or starting with an E, electromagnet, same thing. And therefore, it has a north at one point and a south at the other end. But if it's alternating, what happens to the north and the south? Right, it changes backwards and forwards, it flips. And the primary coil over here is wrapped around this side. The secondary coil is over here. How does the flux get from the primary coil to the secondary coil, according to this diagram? What is this square representing here? This, right, yes, this here is representing the iron core. What does the soft iron core do? It directs the flux, stops flux leakage, or doesn't stop it but minimises it, just to make it more efficient. So this here is, this here is the iron core. This here is the secondary coil. Okay. Now, just because one coil looks bigger than the other does not automatically mean it is a step up or step down. We can have one coil which is this large and another coil which is just slightly smaller, but this could be a step up because it depends on how thick the wires are. All wires come in different thicknesses. Some are really thick wires, and that might only have 10 on this side, and this might have 100 very, very thin wires. It's the number of windings which is important, not the size of the coil. Okay? Rightio. So we are told in this here that the following ideal means we are going to assume that in the primary, all the flux from the primary goes into the secondary, and you're not going to lose any energy through flux leakage or heat. The transformer has 5 in the primary, so the number of windings over here is 5, and we have 10 windings in the secondary. Okay, is it a step up or a step down? Up, good. Now you've told that this is 30 volts in this side, okay? What's the factor of the step up? Right, so it says calculate the voltage in the secondary coil. You don't really need to calculate. What can we write down as the? It's 60 volts. Good. You're told that in the primary coil there is 2 amps. What would be the current in the secondary coil is what I say? It's 1 amp. What must these be together when you do it? Right, you multiply them together and it's got to equal 60. So we calculate, it says to calculate the power in the primary and secondary coil. The primary in each coil, P equals VI, or IV, depending on what you're used to. And that formula is on the formula sheet. P equals IV, so P equals 30 times 2, which equals 60. And that's the primary. And in the secondary, it's 60 times 1, which is 60. And power is watts. Okay? Okay. Are you happy with that one? Okay. Could I get you now to attempt the next one? Anyway. Okay. I'll go there. I'll read it to you, and then you can have a go. An ideal transformer, this comes from a CSSA trial paper. An ideal transformer generates 40 watts in each of its coils. We know that because that means, what type of transformer does this mean? It is if it has 40 watts in the primary and 40 watts in the secondary, what can you tell me about the? It's ideal, good, okay. So in other words, you can apply the mathematics to it. The voltage in each coil is measured by a cathode ray oscilloscope, or probe. So there we are. In the secondary coil, the voltage is 80. The current in the primary coil is 2 amps. Okay? Right, note B. The diagram does not indicate the number of windings in each coil, so you can't count 1, 2, 3, and so on. Okay? Well, yeah, okay. You are asked to determine the AC voltage supplied to the primary coil. Secondly, in B, the secondary coil has 100 windings. Determine the number of windings in the primary coil. And C, you have to identify the purpose of the iron ring. All up, this was only worth 3 marks. Off you go. Okay, let's have a look at the solution to this. You have to remind yourself that you know there are 3 values to which you can work with. You can work and say that the power in the primary and the secondary coils are the same. You have to then work, if you know, you always know that that is true. If you know the ratio of windings, you can work out whether it's a step up or a step down in voltage, or you can always work with current. So you can work with voltage, you can work with current, and you can work with power. And all of those 3 things can work together. So we have to work out the AC voltage in the primary coil. We know that the secondary coil, so let's just draw it out that way. Don't care if there's any difference in the size. That's the primary and the secondary. We're going to put on what we know. We know that the current, the voltage in the secondary coil is 80, and the current in the primary coil is 2 amps. Okay? And we know that each of them has 40 watts. Okay? So we know that this number up here times 2 equals 40, and we know that this number here times that number there also equals 40. Okay, because we know that P equals IV, or VI, in both coils is the same. So can we now quickly work out what is the AC voltage in the primary coil? Well, what times 2 is 40? 20. So this must be 20 volts. So I now know that. Okay? If I know that that is 20 volts, do I know this is a step up or a step down? Up. And what's the factor of the step up? It's a times by 4. Okay? So if it's a times by 4 in voltage, it must be a divides by 4 when it comes to current. Okay? So we're asked to find out the number of windings in the secondary coil. Sorry, no we're not, the primary coil. If this has 100 windings in this coil here, that's going to have a times by 4 value to the number of windings in the primary coil, what must the primary coil have? 25. Okay. And finally, what's the purpose of the iron ring? Right, to direct no, not the current. Flux, yes, the magnetic flux, the lines of flux. Okay? And from one coil to the other to make it more efficient. Okay, now notice the secret that well, this is not but a lot of us have discovered. The secret is to draw the 2 symbols of the primary and the secondary side by side, and then add the numbers above and below it. Okay? And you know that this times this equals that, that times that has to equal that, and then you can work your way around. Okay? And use arrows saying times by 5 and so on. There are formulas for all this, but the formulas that I use are just, why bother to use a formula? There's no need for formulas. Okay, it's terrible if you use a formula for this. It's so bad. Okay, can I get you now to have a go and do 3, 4, and 5 on that sheet, please?